I'm going to continue the series of videos on solving circuits in the phasor domain. And so look at a couple of examples here on node voltage and mesh current. So we'll just kind of summarize some steps here. First of all, if a circuit's in the time domain, it's got to be transformed to the appropriate frequency domain. So in other words, we've got to do a phasor transformation. So the steps are, as we've seen in a couple of examples already, we want to transform all known and unknown voltages and currents to phasors, either known phase and magnitude or unknown phase and magnitude. We'll replace the component values for resistors, inductors, and capacitors with their impedance values, and you can ignore this mutually coupled coils. That's a circuits 2 thing. We'll then follow along in the steps of the basic analysis method that we learned in just typical mesh current and node voltage methodology to find the unknown current and voltage phasors of interest. And then once you solve for the answer in the phasor domain, you then transform it back to the time domain to find the steady state or time domain currents and voltages that were requested. So here's an example of the use of the node voltage method in the phasor domain. In this case, some currents are labeled, and those are the ones that you want to find. So the first thing that you do is you transform the circuit into the phasor domain, which means IS becomes a phasor. It would be 10.6 angle 0, which we can just use 10.6. The 20 I sub x becomes 20, and I of x becomes a phasor. The three resistors remain the same. The inductor will go to j omega L, and the capacitor will go to minus j over omega c, where omega is 500. So if we do that first, we then come up with the circuit in the frequency domain, where here's the transformation on the inductive impedance and on the capacitive impedance. And so let me remind you one more time that the capacitive impedance will be negative. That's how you know it's capacitive. An inductive impedance will always be positive. Okay, so here is our circuit, and now what we're going to do is define two node voltages here and here. In the examples that I've worked in the past, I've defined a node voltage at a voltage source. In this particular example, they leave that undefined. The ground is placed at the bottom, but we know that the voltage at this node would be 20 Ix. So in the node equations, you're only going to see a V1 and a V2. And then V3 equals 20 Ix is going to be automatically substituted into their equations. So once again, here's the circuit, here's V1, here's V2, node 1, node 2, ground node. And so the first node equation has the current coming into the node, V1 over 10, V1 minus V2 over this impedance. The second node will have V2 minus V1 over this impedance, V2 over minus J5, and then V2 minus 20 Ix over 5. So those are your two node equations. Then you need an equation that defines the dependent source variable Ix. Ix is the current between node 1 and node 2. So that would just be V1 minus V2 over that total impedance. So that's node voltage. Now I believe what I did next is in the example that I took this, in the text that I took this example from, they just immediately jumped to giving you solutions for V1, V2, and Ix. I know many of you have struggled with solving simultaneous equations, and I think some of you are struggling now with complex numbers. So I think what I have on the next slide is an illustration of how to use Cramer's rule in MATLAB in order to find solutions. So let's see if that's indeed what I did. Yep. So the first thing I did is I took the equations and I rearranged them so that I have the V1s, V2s, I've collected like terms. And then rather than doing the complex number math myself, I'm going to enter these into a matrix in MATLAB. So what we're going to construct first, according to Cramer's rule, is the coefficient matrix. So the first row of the matrix will be the coefficient for V1, the coefficient for V2, the coefficient for Ix, which in this case is 0. The second row of the matrix will be, once again, the coefficient for V1, the coefficient for V2, the coefficient for Ix. Third row, same thing. Okay, so that's how you construct what's referred to as the delta matrix in Cramer's rule. Then if you want to solve for V1, into that same matrix, you insert for the V1 coefficient 10.6, 0, and 0 respectively. And then for V2, you would do that substitution for the V2 coefficient, and for Ix, you would do that same substitution. And then the solution will be the determinant of those respective matrices divided by the determinant of the coefficient matrix. So that's what's going to go on in the MATLAB code. And of course, it's perfectly legal and legitimate if you want to use MATLAB to solve for simultaneous equations using complex numbers. I think that is a great idea. So you can retype my code into MATLAB and make the appropriate substitutions for anything that you're trying to solve, and it should work fine. So the first thing I did was to construct the delta matrix. As you know, hopefully, if you're inputting a matrix into MATLAB, the first row, the elements are separated by columns. In MATLAB, you cannot use J, you have to use I. It recognizes I as the imaginary. And so basically I just used appropriate syntax like you would do in any programming language. You do not have to separate, most of the time in MATLAB, you do not have to separate your row elements by commas, but to me it makes it a little cleaner to proofread. So in this case I did separate my row elements by commas. And so I entered each element individually, and then the semicolon tells you go to the next row. So this is just the coefficient matrix that was shown on the equations on the previous page. I then intentionally left out the semicolon so that I could see the matrix it feeds back to me and make sure there aren't any errors. And then I did the same thing for V1, except you'll notice where originally I had this V1 element being the coefficient of V1 in the equations, I substituted the answer column or the constant column. So I ended up with a 10.6 here on V1. V2, same thing, except the substitution goes in the second column. So here's my 10.6, my 0, and my 0. And Ix, the same thing. So I had it feed me back those matrices so I could be sure there was nothing weird or strange. And then I just defined, in order to solve, I defined something called V1 value. I took the determinant of the V1 matrix divided by the determinant of the coefficient matrix called delta, and I got outputs in complex number form for V1, V2, and Ix. Now, the answer given in the textbook has a little bit of round-off difference. I'm not sure why that is. Maybe I had a slight typo in one of my matrix entries. I don't think so. The current value is almost exact. V2 is very, very close. V1 was off by what appeared to be a little bit of a round-off error in the real part of the solution. But like I said, you can do this on MATLAB. You can also, I don't know if Wolfram Alpha, I know Wolfram Alpha has a tool, a user interface that will easily solve a 3x3. I don't know if it'll solve it with complex numbers. I've never actually tried that. So I just coded this into MATLAB. There's also a way in MATLAB to convert from rectangular to polar form. Off the top of my head, I don't remember the command. It's not one I use very often. But you could certainly go into the help in MATLAB and look for that. And for those of you who had 1304, you may already have that command on the top of your head. All right, so that gives us then the phasors for V1, V2, and Ix. And then you can get the currents that were requested, IA, IV, and IC, in the problem by taking by just applying Ohm's law and the other typical circuits laws when needed. So I'm not going to go back to compare these equations to what was drawn on the circuit. The main point of this example was to show you how to implement Cramer's rule on MATLAB and the fact that this can get really, really messy. So here's what you get when you actually solve for those branch currents IA, IB, and IC. And so the next point of the example is, okay, here's our solution, 7.04 angle minus 13.8. That is in the phasor domain. To convert back to the time domain, we take the magnitude and we take the phase, and we just substitute that back into the time domain. Here's the magnitude, here's the phase, here's omega t. And you do that for all three of the values that were requested in the problem. So no deep thought involved in going back and forth from time domain to phasor domain. It's just a simple matter of finding the magnitude, finding the phase, being sure you have a cosine function, and realizing that within a circuit all of your frequencies will be the same. Okay. Sometimes a circuit that has already been transformed into the phasor domain. So that's an example here. I believe, let me check. Yes, the goal of this example is to illustrate the mesh current method using in the phasor domain. And so in this particular problem, the circuit is shown as having already been converted. And so what you're being asked to find is V1, V2, V3, and IX. Or V1, V2, and V3. So we're going to use the mesh current method to do that. So we're basically just going to define two mesh currents, I1 and I2, and we're going to utilize Ohm's law, where the only difference is instead of resistors, we'll have impedances. So we're going to use Ohm's law and the mesh current method in order to write these two mesh equations. So for example, if we come around this mesh, we have minus 150 angle 0, and then we have I1 times the phasor 1 plus J2, and then we have I1 minus I2 times the impedance 12 minus J16. So that's the way that's going to work. And here are those equations where the 150 has already been moved to the other side of the equal sign. So the source is just being shown in the other source column. So those are those three equations. We also have to have an equation for IX, the dependent source equation, and that one is obtained by looking that IX is pointed in the down direction, the same direction as I1. So IX is I1 minus I2. Okay, so taking these three, now I did not solve this one using MATLAB, but you can see how if you moved IX to this side of the equation and put a 0 here, put all these constants on the right-hand side instead of on the left-hand side, rearranged and collected like terms, you could very easily write this in terms of matrix and use Cramer's rule. However, when you solve, these are the solutions that you get. And now before you can represent anything in the time domain, what do you need to know? Well, you're not actually given all the information you need in this circuit to convert it back to the time domain. So as you look, let's go back. So here's the circuit we were given, and so I'll ask you to kind of think. If this were a class, I would stop and make you answer my question. I'll ask you to think about what it is that we don't have in order to be able to go from this solution that we obtained in the phasor domain back to the time domain. So we could certainly take this I1 and we could put it in polar form, so we would have a magnitude and a phase, but what are we missing? What we're missing is omega. So if you start with a circuit in the phasor domain, you cannot transform it back to the time domain unless someone tells you what the frequency was, because that's going to be an important part of doing the inverse transformation. Okay, so then you can use, you can basically use I1, I2, and I3 in combination with Ohm's law to find V1, V2, and V3. And then you can use these to solve for the value of the voltage for the dependent voltage source. So that's an example of how to utilize the phasor method along with mesh current. At this point, I will comment that I'm going to want you to practice some of these, so I will give you some homework. But on the exam, You will have the opportunity to utilize MATLAB or a calculator to do some of the simplification. My goal is not to retest you on mesh current and node voltage method. It's to test you on AC circuit analysis. So be ready to do these complex number calculations and solutions. I'm going to try to keep the problems a little more simple, where we would at most have a 2 by 2 matrix if I actually ask you to solve it. So once again, important to be sure you know how to do the complex number manipulation, so that if you should have a problem like this, and I would say it would be more likely that it would be 2 equations and 2 unknowns, that you know how to solve that, and that you're not trying to do this all by hand, that you have some method that you can rely on to help you, as you know, from a calculator standpoint, to solve matrices like this or solve simultaneous equations like this. All right, that concludes the examples that I wanted to show to get you started as far as how to use our conventional circuit solution techniques. We have almost reached the end of the material in the class. The remaining material in the class will be for me just to reinforce you on some of the concepts and prepare you for the third exam, as well as AC power. So those are sort of the remaining topics that we'll have. So I'm going to go ahead as soon as I have them available and release the AC power lectures, as well as release the final problems, because our last exam will have to take place on the last legal day to give an exam. So we will have to have exam 3 before the Monday of the week of Thanksgiving. So I'm working on that so that we don't conflict with the statics classes of Dr. Dan Miller, and be sure that I give you a range of times so that should he schedule a class exam on that Monday evening, you have plenty of time to do both exams. And you have some flexibility of choice over exactly when you take my exam. All right, so that concludes the lectures for the week, on at least sort of presenting some examples on how to solve circuits in the phasor domain. I want to produce one more lecture where we do some summary. When we get to AC power, we'll discuss phasor diagrams and leading and lagging again. We talked about that, but I want to reiterate that some more. So, and then we'll have some discussion on what will be on exam 3.